Now, we're all programmers and we're used to the idea of random number generators, rand functions that we can call in different programming languages and get random numbers. So what's the connection between that and all this probability we've been doing, which has all been coin flips and rolling dice and whatever, and not really much to do with software. So how do we get those random number generators in software is one question. And the second question is, can we use them to simulate to experiments? So for example, if we want to simulate what happens when we toss a coin 1,000 times and calculate the number of heads, right? How's that distributed? Could we actually get a program that kind of fakes it up and pretends itself? We have for loop for y equals 1 to 1,000. Let's flip a coin, count the heads. Can we not do stuff like that given a random number generator? And how do you do that? And that's the big important idea. I'm only going to talk very briefly about it, but it's much bigger than I'm going to talk about. It's if you're ever, it's often the cheap thing to do, rather than thinking very hard about doing your calculations, just write a program to simulate experiment and count things up and to estimate the probabilities. And it's often a fast, cheap way to do things. Or if you've managed to do the calculations and you're not sure about them, you want to check them, it's a way to double check things as well. So it's a really powerful, important thing. Even though I'm not going to labour it too much, it's probably should get more attention inside the module. Okay, so how can we, let's start by thinking about Bernoulli random variables. And suppose we have a random number generator. So let's start with the simulation and then we'll worry about the random number generators in a minute, where they really come from. Suppose we've got a random number generator that picks an integer between 0 and max, and 0 and 2 to the 32, uniformly at random. Suppose that exists, and we'll see shortly how you generate such things. So we understand that that's a discrete random variable. It takes a lot of values, 2 to 32 values, but that's okay. And then we divide by maxint to get floats between 0 and 1. But they're still discrete because it's not actually, there's quantization. We only have 2 to the 32 values, so it's not properly continuous. It's just discrete, but lots of elements. So it fits inside our setup we've been thinking about up till now. Now, if you're running a program and you are interested in doing this sort of thing and trying to simulate experiments, it's always a good idea to have a quick check at the random number generator and see if it's any good. So because they're not always good. So here's an example, and here's how you do that, right? It's super simple. Here's an example from MATLAB. So this is, I generated 1 million samples, uniformly distributed between 0 and 1, and then did the histogram, plotted the frequency of all the different values in bins here, right? I just use the program. So here's the MATLAB code down here, right? It's a one-line piece of code. And you can see it's pretty good, right? You get roughly 10,000. There's little blips back and forth, but it's pretty much even, right? All of the different values look like they're about equally likely, which is what we expect. So that's quite a good random number generator. But they're not all great. So how do these random number generators really work? So sometimes, if you really want good randomness, you might have a sensor and actually connect to something physical. Or so you might look at temperature or something like that. Or you can use something that's sometimes used for generating keys, cryptographic keys, is you press some keys on the keyboard and the timing of your keys is a source of randomness. Your finger presses are the time between them is like a physical source of randomness. And there's things like that that can be used to generate random numbers from the environment. But that's expensive and it's slow, right? It's hard to generate a lot of those random numbers. So the cheap and nasty alternative, which is lower quality generally, but it means you can do it fast and generate large numbers of random numbers quickly, is to use pseudo-random number generators. And here would be an old style one. They're really, really simple, right? You can go and implement this and try it. So we've got a couple of magic numbers. So A there, this is a special magic number that someone just tried, right? There's no theory particularly behind it, just tried it. C is a very special one, 1, 2, 3, 4, 5, right? So we have a seed, so initially x0 is our starting point. We plug that in, we take A times x0, add C, and take mod 2 to the 31, right? just to make so it wraps around and stays with it with our set of integers. And that gives us our new random number. It's not a random number, of course, because we calculated it, but we're going to use it as if it was. And then we take our new one. If we want a new random number, a third one, or a second one rather, we take that one, plug it in, and we can keep doing that, keep feeding it back in, and get as many random numbers as we want. It's a nice short equation. We can generate them really fast. Now this is used by glibc traditionally, and the quality is pretty bad, right? It's really rough and ready. So here, if we generate 1,000,000 samples and plot the distribution, you can see, it's 100,000 samples. There's the code at the bottom. You can see, so the bins should all be about 1,000, but you can see some are a good bit higher, some are a good bit lower. So it's nothing like quite as even as the MATLAB random number generator. So it's rough and ready, it's fast. If you just want quick calculations, it's all right. But if you care about good quality random numbers, you wouldn't use that. So there's much better ones. So for example, Python and MATLAB use a thing called the Mersenne twister. If you Google that, you'll see it's a Wikipedia page, and basically instead of having just a one-step equation here, it's a two-step equation. It does one calculation, takes the output from that, feeds it into a second one, and so on. And that's what the MATLAB plot was. Still pretty fast. If you want a still better random number generator, then you do something specialized. So the crypto guys do specialized things. And that is important in crypto, that the random number generator is good, because your security is based on a presumption of randomness, and so if it doesn't hold, then all your security is compromised. And in fact, the random number generator was one of the vectors of attack a few years back by the NSA, who standardized a weak random number generator, where it was quite easy. Once you saw, I think it was 32 observations from it, you could guess what the seed was, what the X0 value was, and from that you could generate the whole sequences again predictably, and so it completely defeated the idea of randomness, the protection provided by randomness. Of course, people are now very careful about those random number generators for the crypto stuff. Okay, so there's no magic to pseudo-random number generators. They're just random-like in that they're not random. We're generating them in a deterministic way, but they behave kind of in an unpredictable kind of random way. You look a little bit like random variables. They're good enough for doing rough calculations. If we want something better, we'll go and take some values from the environment, something to do with heat or thermal noise or heat presses or something like that, to try and get better randomness. So let's suppose we've got a good rand function, good enough for our purposes, that gives a value between 0 and 1, uniformly distributed. Well, we can immediately use that to generate Bernoulli random variables with parameter p. So we take our u here, that's our value, it's a random variable between 0 and 1. So we take a draw, right? We make a call to our function, our rand function, to get a value there. If the value is less than p, so less than 0.1 say, or whatever our parameter up here is for our Bernoulli distribution, then we say x is 1. And if it's bigger than p, we say 0. And that'll give you a Bernoulli random variable with probability, with parameter p. And so when I try that, here's the code at the bottom of MATLAB. Then here's what I get. So if I repeat that, how many times here? 1,000,000 times. And look at the frequency, I can see I get 10,000 times, 100,000 times, I get a 1, and 900,000 times I get a 0, right? So the probability of getting a 1, the fraction of times I get a 1 is 0.1, which is what I want, what I expect from my Bernoulli random variable. And so stop, why is this working? Why is this trick here working? It's a nice trick. So if you stop and have a think about how the random variable u behaves. So this is its distribution. Remember, it's between 0 and 1. And all the values between 0 and 1 are equally likely. And then suppose we draw our line. That's a banana, but we'll just live with it. At p, draw it there. Now you can see all of these values are equally likely, and what we're saying is that if it lands here less than p, then we're going to give a 1. Now you can see p, this area under here, this goes from 0 to 1, right? This is suppose this is normalized, right? Then the area under here is a rectangle, a square rather, side 1, height 1, so it's 1. And this area under here, under the first p part, is a rectangle, which is of length p, height 1, so that's of area p. And so the fraction, you know, all of those little bins, right, that we were drawing there, so the fraction of times that when we draw what we expect to land in this area is going to be p, right? And the fraction where you land above p is going to be 1 minus p. And that's exactly a Bernoulli random variable, right? So we can map from our uniformly distributed random variable to a Bernoulli one using this nice trick. And once we have a Bernoulli random variable, you know, it's a really basic thing that we can use in lots of ways. It means we can simulate coin flips, bit flips, and all sorts of processes of that sort. And it's just straight away, really in a really straightforward way. And once we've got Bernoulli random variables, of course, we can get binomial random variables just by taking a collection of Bernoulli ones and adding them up. So here's the code for doing that. So we calculate take our random number, we generate n random numbers. We take x equal to 1 if they're less than p, less than or equal to p, and bigger than and equal to 0 otherwise. So this does it in one step for a vector, so it does it for the n. Then we add them up. And that y here, so these guys here, this is a vector of n Bernoulli random variables, so that's our n trials. This y here adds them up, so it's a binomial random variable. And then we repeat that 100,000 times to get 100,000 examples of this y variable, this binomial random variable, and then plot the distribution of that, the frequency. So here's the different values. You can take a value between 0 and 10 because we're adding up 10 Bernoulli random variables. That's the only possible range of values we can get. Here's the measured frequency. You can see the most likely value is 3, and then it decreases as we go either side. And if we go and calculate, use our formula and plot it on top here, that's those circles, it's bang on, right? So it's a nice, once we have a Bernoulli random variable, we can get binomial random variables, and we're in good shape. And we can also do this, we used this trick of checking against p to get a 0 or 1 value, so a Bernoulli random variable. We can also use different thresholds if we are interested in rolling a dice with 6 values. We can take our area, our length between 0 and 1, where our random, our rand function returns values, and divide it into 6 equal size sections, and then use that to generate something like a dice roll with 6 values. We're not just limited to getting 0 or 1 values. We can also do other things.